Hi folks, welcome back. So this time we're going to be mostly on the breadboard. We were over on the whiteboard most of the time last time, so in the interest of kind of just getting on with it, we're just going to try and do the more practical side of what we were doing last time, which was looking at RC filters. So just a brief recap, we went over how you can use a resistor and a capacitor in a kind of frequency dependent voltage divider configuration which behaves as a low pass or a high pass filter. And today we're going to build a low pass filter, and then we're going to look at some of the issues around the thing that we build, and then in another video we're going to go on and we're going to build an active filter, which is way better, so stay tuned. So we're going to hop straight down onto the breadboard where I've got something built up. So here we've got this 4106 oscillator, which is just like we built up in our first video, and we've used it in several videos, so go back and have a look if you don't know what I'm talking about. So we've got the input, we've got the resistor feeding back to the out. We've got the input, the output, and we've got the resistor feeding the output back to the input. And then we've got this wire here which goes away to, it's currently plugged into the scope. So here's the note we can hear, just like we had last time. Okay, so now if we go onto the scope, we can see that this tone, put it quietly, we can see two different representations of it. And they tell us different things about how the signal is behaving, what it sounds like. So we got this representation here, which we call the time domain view, where this axis here is the amplitude of the signal, and this axis here is time. And here we've got the frequency domain view, where this axis here is still amplitude, but this axis here is frequency. So we can see that we've got a spike here, and then lots of smaller spikes that kind of decay down into this is just like noise. And so this view we're probably somewhat familiar with, kind of a sound wave. This is kind of what different waves look like. Different things have different shapes on the oscilloscope, and you'll come to learn them all. But this view is slightly more abstract, but actually a lot more useful for what we're doing. So we can see this fundamental frequency here, which is the lowest and strongest frequency here. Strongest because it's the biggest in amplitude, it's the highest one on this plot. And that's what tells us what note it is. So if this is a square wave, so it sounds like this. If I had a piano or a flute or any other almost any other instrument that played the same note, it would have this same fundamental frequency, but all these other frequency partials, we call them, or harmonics, are overtones that give us the character of the sound. So we can see here there's lots of these little kind of high frequency partials, and it's kind of hard to see, but you can see their relationship. As I increase the pitch, the high frequency partials spread out, and that's because they're like mathematically related to the fundamental. So as the fundamental slides up and down, which is increasing and decreasing in pitch, so anything that's 2 times the fundamental frequency is obviously going to increase twice as much. For every 1 hertz increase in the fundamental, the second harmonic, which is 2 times higher, is going to increase by 2. Third harmonic is going to increase by 3. So that's how you see this spreading out. Okay, so what we're going to do now is we're going to build a simple filter that's going to filter out a lot of these high frequency partials, and we'll show you a before and an after of what that looks like, and then we'll go on to have a look at a slightly more usable filter. So before we build this up, let's just take a second to think about some of the practical considerations that we need to make when we're thinking about building anything. So we need to come up with some criteria. So the first thing we need to know, which you'll know if you watched my last video, and if you haven't watched my last video, go back and watch it, because you will not have a clue what I'm talking about, unless you already know this, in which case, why are you watching this video in the first place? So what we know is that we can set the center frequency of the filter if we're doing an RC filter, which we are doing. So that means we're using 1 resistor and 1 capacitor. We're not using any op amps, we're not using any transistors, we're not doing any of that fancy stuff just yet. with this equation. So FC, that's center frequency, is 1 over 2, whoa, pi times R times C, right? Easy. So there's too many unknowns here for us to solve. So we don't know this, we don't know this, and we don't know this. So the easiest way is to just pick some known things. So let's set the center frequency at 1 kilohertz. Right, this thing that we've got on the scope here, it's about 408, 490 hertz. So setting the 3 dB point at about 1 kilohertz will give us a nice attenuation of those high frequencies. So, okay, so that's one unknown that we've sorted out. 1 kilohertz. Forgive my terrible handwriting. Okay, so 2 pi, we know that. So now we've got the R and the C values. So usually there'll be some sort of constraint in your design that will allow you to be able to pick one of these. Obviously this is the first thing we're building, so we don't have to worry about it too much. Generally, you want to think about the impedance, the input and the output impedance of your little circuit block and how that's going to interact with the rest of the circuit, which we will go on to in a minute if you don't know what I'm talking about. So for now, we will just pick a 0.1 microfarad capacitor, just because that's a nice round number, and we'll calculate the resistor number and we'll see what comes out. Okay, so we know we've got 1k, so that's 1000 equals 1 over 2 pi. Oh, made the worst. 2 pi R C. And we know C now to be 0.1 times 10 to the minus 6. 10 to the minus 6 because it's microfarads, remember. So now all I need to do is times through by R and divide through by 1000 to get R here and 1000 down here, so I can solve for R. So R equals 1 over 2 pi times 1000 times 0.1 times 10 to the minus 6. Whoa. Okay, so let's get our trusty calculators out. I'm not expecting anybody to do any maths. You know, if you've not got an actual calculator, just download one on your phone or something. Get a calculator. Just get, this is like, I don't know, 10 quid or something. You don't need a super fancy graphic calculator, just something like this. I've had this since I was about 15. Yeah, you know, it'll do you for a long time. Times 10 to the minus 6. So that gives us 1591. So that's ohms. So let's round that to about 1.5k. Okay, R equals 1.5. This has told us that if we have our input signal here, and we have a resistor here, this is 1.5k, and a capacitor here down to ground, and this is 0.1 microfarads, that will get a signal out here that has been, all the high frequency information has been attenuated over about 1k. Okay, so let's build this up and see what happens. Okay, so over on the breadboard here, this is our little output wire here. So we'll take a 1.5k resistor, and then we can bridge this little gap here with the resistor, and then we got 0.1 microfarad capacitor, wherever. And now if we take our output at this point here, so this node here, so that node there is equivalent to this node here. A node is a point in a circuit where two thingies meet. Thingies, that's a technical term. Then we should hear a filtered output, so the high frequencies should be filtered out. And if you don't know why, go back and watch my last video, because I go over it all in depth. frozen the scope. So now we can hear the attenuated audio. And now I'll unfreeze the scope. So what we're looking for is we're going to see a big change in the shape. So generally when you see sharp edges like this, you think high frequency. So we should have softer edges. They'll kind of come up like this, like a kind of rounded off triangle. And we should see a lot of these high frequency information lower down, and we should see not too much attenuation of the fundamental frequency here. Okay, so let's have a look. And that's what we see. We see the fundamental frequency went down a little bit because we are that 1K cutoff point. It's not like a brick wall. It gradually goes down towards 1, and at 1K and after it continues to attenuate more and more. So there you go. That's exactly right. That's exactly what we designed, and that's exactly how it came out. Now the problem with this, that you may have noticed if you have a keen ear, is that this filter is affecting the oscillator. If we listen and have a look to the signal, right, so this is what it looks like. So if I unplug the wire that connects the output of the oscillator to the filter, we'll see it slightly changes in pitch. So there we're about 480, and here we're about 450. It's kind of wobbling around a bit because I'm touching it. About 450, and then we'll go back up. Now the reason for that is that this chip can only provide so much current. So remember, let's have a look at what's happening at the chip, because we didn't actually draw the chip connected up. So we got from our first video, if you cast your mind back all that time ago, we have, this is our little inverting Schmitt trigger doodah. Ah, mate, this is the worst. Try and draw it a bit better. I'm right-handed, so this might go even worse. So here's our Schmitt trigger. This is our pitch control pot. Here's our capacitor going down to ground. Right? So this output here is also connected now. To our filter. So before, all of the current that this could provide was going through this resistor and down to here. Now the current coming out of here is going this way like it was before, but also has to come down this way to kind of power these components here. So the problem that we're facing is that as we attach this, it draws a little bit of the current away, so this charges this up slightly slower, which is what drops that pitch down, and that's a problem. So the reason why this is happening is that this impedance is too low, so it's drawing too much current. That's what I was talking about. The input impedance of this circuit is too low. Generally speaking, when we're talking about input and output impedances, if you're transferring voltage, which we are, you want the output impedance to be very low and the input impedance to be very high compared to whatever it's driving or being driven by. So we want the combined impedance of this part of the circuit to be at least 10 times more than the output impedance of this, which it probably is. The output impedance of this is the output impedance of this op-amp, because the op-amp is short-circuiting this impedance. You know, when a very low impedance is connected with a relatively high impedance, you know, the output impedance of an op-amp is in the tens to hundreds of ohms. And, you know, we know that this is 1.5k, and I'll go into that in a second. So that's why it's a very subtle thing, but as we change this, and if we put a variable pot here, as we decrease this, because we want to change the cutoff frequency, don't we, if it's a filter, and so to change the cutoff frequency, we change this resistance. So as we dropped the impedance of this loading effect would get worse and worse and worse. And so we would have to have this higher and higher and higher you know, the lowest bound of this would have to be higher and higher and higher, but then the output impedance of this section gets higher and higher and higher as well, so that you've got a massive problem. And that's why op amps are so good, because the input impedance of an op amp is very high and the output impedance of an op amp is very low. So what we're going to do for now is we can cascade this into a second stage of the op amp just as a buffer, so that this doesn't load this down, but we will shortly go on to building transistor circuits and eventually op amp circuits that can kind of compensate for this, or do a thing called impedance transforming, where we can make the impedance what we want it to be. Hi guys, just editing into the video because I realised I've missed something out. So I failed to mention about the input and output impedance of this circuit. I said I would earlier and I forgot. So the reason why the input and output impedance is important is because, as I said earlier, that you've got these things called loading effects. So essentially, if our op amp is a thing, right here it is, and it has some sort of impedance, and we'll go into how to calculate impedances of all sorts of different things in another video, but right now all you need to understand is that we can think of this whole circuit as just an output impedance for the purposes of modelling the rest of our circuit. So we've got our little output impedance, and then that is going into our high pass filter, which we can then model as its own impedance, its input impedance, and the ratio of those two impedances act as a voltage divider. So you want the input impedance of your filter, which is this part here, to be as high as possible compared to the output impedance of this part here, because then the most ratio of voltage is dropped over this part, because that's how voltage dividers work. If you don't understand that, go back and watch my Circuits 101 video where we go over how voltages and currents and stuff work in series and in parallel. So what did I mean that the for this circuit the impedance is always just R? Well, it's not always R, because the impedance of the capacitor changes depending on the frequency of the signal. What I meant was the only values that you care about is R, because all we care about as engineers is making it, if we calculate what's going to happen at the worst case, then we're always going to know that it's always going to be better than that. So what's the worst that an input impedance can get? Well, what that means is how low can it possibly go? So if you look at this signal, this circuit, sorry, right, we've got these two elements, and that's the output. We don't care about the output because we're looking at the input, and this is a really important kind of facet of circuit analysis. We're this little circuit person and we're looking in this way. So let's forget about the output for a second. And so if we look, as a signal, we're going to go this way and down to ground. And we're going to drop some of ourselves over this, and we're going to drop some of ourselves over this. So how low can that go? Well, we know at high frequencies, this is going to act like a short circuit. And that's obviously going to be the lowest that it can be, because this can't change, it's a resistor, it doesn't change its impedance with frequency. But this value will change with frequency, and when it acts as a short circuit at high frequencies, essentially when your XC gets very small, the series combination of these two is at its lowest, because no matter what impedance this is, don't even worry about calculating it, you know, doing all the complicated maths to calculate the impedance and adding them together. You just know any impedance is more than no impedance, so the series addition of these two impedances is going to be lowest when there's only one. And so now we look at it from the other side. So now we think, what's the worst case that an output impedance can get? Well, output impedances, we want them to be nice and low, so that we're not having to go, right, that because the thing it's driving has to be 10 times greater than it to get this nice ratio voltage divider thingy we spoke about a second ago. So if the output impedance of this is really high, then the input impedance of the next stage has to be really high, and then the output impedance at that stage is going to be high, so then the input impedance is the net, and you get this like horrific exponential growth of impedances, and it's a real pain. So when we say how bad can the output impedance get, we mean how high can it get. So now we're looking this way, right, little circuit dude, we're looking this way, so now we see we've got two paths, and when you see you've got two paths, right, you know that you're in parallel. So what's the lowest that a parallel, what's the highest, sorry, that a parallel impedance can get? Well, a parallel impedance is highest when, again, this is, when, not again, sorry, when this is an open circuit. When this is an open circuit, then this impedance doesn't shunt this impedance at all. So this impedance is just R, with no impedance to parallel, the parallel resistance would decrease the resistance of these two combined pairs. Again, go back and see my other video if you don't understand what I'm talking about. So at low frequencies, this presents an open circuit, and so our worst case output impedance is also R. So if we know R, we know the worst case output impedance, which is the only output impedance we care about. If we design for the worst case, then it will only be better than that. And we know R is our worst case input impedance, and we design for that, and it'll only be better than that. So whenever you're looking at any circuit and thinking about input impedances or output impedances, think about how bad can it get, what's my signal extremer, you know, what's my lowest frequency, what's my highest frequency, and think about how your circuit is going to react, and then you don't even need to go into all the maths and all the complicated impedance and complex numbers and all this kind of stuff. You can just build up an intuition for it like this. So back to the normal video. Okay, so now to just wrap this video up so it doesn't go on for too long, I'm going to take my little signal. So here we're going to take the output of this and we're just going to run it straight into the input of this next one. Rah. And then I'm going to take the output of that and I'm going to go over here, and this time instead of this 1.5k resistor, I'm going to put a potentiometer. What have I got here? 50k, that'll do. 0.1 microfarads. And we'll take the output again on this node here, and we'll have a look on the scope at what happens. So we can hear now we have a nice controllable low pass filter that doesn't affect the pitch of the signal at all. And as I said in the previous video, the theory for this, for a high pass filter, is exactly the same. You just swap the resistor and the capacitor around. So there's one more big problem with this circuit, which is that when the filter is very low compared to the pitch of the sound dims a lot. The volume of the sound dims. So like, that's really loud, and then as I filter it away, it becomes really quiet. We don't want that. And what we want is a thing called an active filter, which simultaneously does the filtering and it compensates the gain, so it turns the gain back up afterwards, so we're not having to like fiddle around with loads of different knobs to get a consistent volume. Because, you know, if you're doing this in a track, you're not going to want that as you filter stuff away. You're not going to want it to get like inaudibly quiet. You know, a little bit of a volume attenuation is okay, but this is like, I'm talking over this and you can barely hear it, whereas when it's at fully open, it's really loud, and if I try and talk over it, you can probably hear me, but it's loud. You know, if you're doing this, if you have an LFO doing this in a track, it's going to sound weird. You know, you're not going to be able to hear the low frequency, so it's going to sound like a volume swell, which is an effect that you can use if that's what you want, but you want the option to not do that. So next time we'll come back, we'll look at some more of this theory, we'll go on to active components, well, specifically an active filter using similar techniques to what we've used before with CMOS chips, because I don't want to get too ahead of ourselves. And then further down the line we're going to get into doing transistors, and then we can look at impedance transforming, which we kind of touched on today but kind of glossed over by just doing this buffer thing, which is useful but a bit of a hack. So yeah, I'll catch you next time. Thanks for watching. Make sure you like, share, subscribe, do all that stuff. Ring the bell. Find me on social media, on Facebook, Twitter, Instagram. Watch more of my videos. Here's some over here. And I'll see you all next time. Take care.